right, good morning, everyone. So last time we introduced we talked about the perspective projection, which is an important step of the graphics pipeline, maybe one of the most important steps because it deals with bringing the abstract 3D representation that we have of our scene onto the 2D visualization on our computer screen. And we saw that this process, although it is of course a fairly complex process, can be split into very easy, or most of them are rather easy, simple sub-steps that can be done with matrix multiplication. In fact, there was only one step that was a little more complicated, where we had to introduce or extend our concept of homogeneous coordinates. So to make it also with matrix multiplication. So we started by specifying the position of our camera and then by a so-called I vector. Here we go. And then the direction of our camera with the gaze vector, and then the specification of the viewing window. And then we said, of course, it's easier to calculate or do the projection if the coordinate system is at the origin of the camera and points towards the scene, or one of the axes points towards the scene. So we did this transformation from world space to camera space. And then, of course, we said it's much easier to do the projection if we have an orthographic projection instead of a perspective projection. So we did this little trick to introduce a matrix. We extended our matrix framework in a way that allowed us to do this transformation in a way that the relative sizes of the objects are preserved. So we can do an orthographic projection, which is of course very simple. And then we did another modification from the orthographic view volume to the so-called canonical view volume to keep the values between -2 and 2. And then the last step was just a simple simple scaling operation, because we just needed to map the general form in the canonical view volume, or the general representation, to then the specific case that we have in our implementation. That of course depends also on different systems, because some systems have a higher resolution, or if you resize the window, of course you have to adapt also the way you scale the objects onto that in that window. Good. So we've seen that this is actually something we can do very easily with a sequence of matrices, or combine those matrices into one big one then in the end. But of course we also made a couple of simplifications, which is basically what we want to talk about today, or two of them we want to talk about today. The first simplification that we made was, we said so far we assumed that the triangles are always inside of the view volume, so we excluded cases like this where triangles are outside of the view volume, and we excluded cases where triangles are partly inside the view volume and partly outside. And we need to do some special treatment here, which is a process called clipping that we will discuss today. Then of course also we said that we are dealing only, or so far we only dealt with wireframe models. That is, we only looked into the vertices, for example, of triangles. Then we said if we project the vertices, then we can draw the lines, and then we have the triangle projected, but only the wireframe version of the triangle, or the grid version of a triangle or a model. But of course we also want to put color on it, and we already talked a little bit about this with relation to shading. We also already talked about texturing, but we will talk about this in more detail in the next lecture, or we get more information about this in the next lecture. But another thing that also kind of implicitly came with this saying we're only dealing with wireframe models is we also excluded another issue we have to look into if we have objects that have a solid color, or that are solid from their structure, because then if two objects are overlapping from a certain viewing direction, then of course we only want to draw one of them on the screen, the one that is in front, or only the parts of the one in the back that are visible from this particular viewing direction, and the other parts we don't want to draw. So this is also something we have to deal with, and it's called hidden surface removal, and this is the second thing we want to talk about today. But let's first start with this case here, where a triangle is partly inside the view frustum and partly outside of the view frustum. And like I said, this process is called clipping, or the way we're dealing with it is called clipping. And to do this, so first of all, of course, we have to find those triangles. And then, when we have them, what we are going to do is we are creating new triangles that are then clipped version of the old triangle. So for example, if you look at the side view here of this triangle, what we are going to do, this is the part that is inside of the view frustum. So we're just cutting off this part and use these intersection points as new vertices of the triangle, and we have a triangle that is completely inside of the view frustum. Or if we have a triangle that intersects with the view frustum in a way that two vertices are inside, then of course we cut off this part here. But then of course the resulting object is not a triangle, but we can by just making a split here on two vertices and opposite sides of the object, we can create two triangles. Of course, we could have alternatively also cut it in this way, but in both cases we cut the object in a way that creates new triangles. Good, but before we do that, of course, we have to find those objects that are those triangles that are intersecting with the view frustum, or that are only partly inside of the view frustum. And to do this, let's just recap quickly the implicit equation of a plane, because we usually represent the sides of the view frustum with plane equations, of course. And the implicit equation of a plane, you remember at the beginning when I introduced all these different notations of different ways to represent planes, I said, yeah, we need different ways to represent them, because in a different situation, a certain representation has certain advantages, and so that's why we need this kind of representation, because it's easier to use. And for the implicit equation, this is now one of the situations where it is really obvious why this implicit equation is so useful. So let's remember that if you remember, the implicit equation is defined by a specific position in our 3D space, which is expressed by this vector p0. And then the orientation of the plane is specified by the normal vector, which is perpendicular to the plane surface. So by giving the orientation of the normal vector, we can give the orientation of the plane, and we have the vector. But of course, these two vectors do not allow us to directly calculate a point on the plane, but we set the implicit equation. It's also named implicit because we cannot explicitly calculate the points on the plane, but we can use it to verify if a point is on a plane. So if we have a point here, P, then of course if we take that point, put it in the equation, you see here we get this vector here, P minus P0, and then we have, P minus P0, that's this direction. Yeah, and then by taking the scalar product, we know that this vector is in a right angle if it equals 0, or the other way around, we know that this vector is on the plane if it makes a right angle with the normal vector, and then so we can verify this by using the scalar product, and if the scalar product is 0, then we know that this vector is indeed on the plane. And we also would know that, or we see then if we take another point here, let's call it P1, then of course we see if we put P1 in this equation, we see that the difference vector here has an angle theta that is not a right angle, and then of course this will be unequal to 0. And we already seen in the tutorials that every time we have a vector that is on the side of the plane where the normal vector points, this function, the value of our equation becomes larger to 0, and if it is below or at the other side of where the normal vector is pointing, then it becomes smaller than 0. So you made a proof in the tutorials that showed that this plane splits our space into a positive and a negative subspace, and of course all the points that are on the plane are equal to 0. And that is of course now this characteristic that we can use to very easily identify and find those triangles that are partly inside of the view frustum and partly outside of the view frustum. Because if we specify our view frustum with planes where the normal vectors always point to the outside of the view frustum, then of course we can just take a vector or a vertex of a triangle, put it in the plane equation, and then we see if it is below the plane, which means in that case inside of the view frustum, or outside or above the plane, which means outside of the view frustum. So we see here, for example, for point A, with respect to this plane L, point A and point B, both with respect to the plane L, which represents the left plane or left side of our view frustum, we see they are both smaller than 0, which means they are both below the plane. So from that plane, it looks like they are inside of the view frustum. But of course, only from that plane. From the far plane, we see if we put A and B into the line equation, we get A is smaller than 0, which means it is below the plane, that is inside, from that plane perspective, it is inside of the view frustum, but the point B is on the other side, so it is outside of the view frustum. So we see here that the intersection, the vertex between these two the edge between these two vertices of our triangle must intersect with this plane F, and that is how we can then identified that this triangle does indeed intersect with the view frustum and is only partly inside of it. Now be careful here, that's why I put this here in quotes, that it says here inside the plane, what actually doesn't really make sense, so it's more an informal specification of it, because with respect to a plane, it only makes sense, of course, to speak about like above or below the plane. But since we use the planes then to specify the view frustum, I'm talking about inside and outside. But of course, you see here, this point B here is outside of the view frustum, but from purely the left side of the view frustum, you could assume that, or from that plane's perspective, let's say, it is inside of the view frustum, or that plane cannot say anything about if it's outside or inside. From that plane, it only can say that it's certainly not outside on the left side of our scene. So, and that is of course important, because you also have cases like this here, for example, where you say, okay, all the points are outside of the view frustum, but the triangle does intersect with the view frustum. But you see here, when you test this with respect to the left plane, and not the view frustum, but the left plane, then you see here, of course, that they are on different sides of the view frustum. So if you would test that with the left plane, then you say, okay, this intersects clearly with the view frustum, so you cut off this part here and have a new triangle, and then you test against the far plane, and then you see, okay, this intersects, this new triangle here intersects again, so I create these new intersection points, have a new triangle, and cut off this part here. So you see, if we're sequentially testing against all the viewing planes, then of course we can also handle this case here, although none of the vertices are inside of the view frustum. Good. Yeah, so we can create these triangles, but to create them, of course, we need these intersection points, and of course we can calculate them. In this case, it's also shows again nicely these different representations of these different representations of geometric objects, how this often makes our life easier, our calculations easier, because when we have 2 points, of course, we can very easily create the line equation that represents, that is defined by these 2, or the line, an equation of the line that is defined by these 2 points. And if we have this in parametric form, we can just put it into the implicit equation of the plane. Then we just have one parameter, and if we solve for that parameter, we get a concrete value, which I called here t dash. And if we put this t dash then in the line equation here, then of course we get this a specific point p of t dash, and this t dash is then, p dash is then our intersection point here that we can use to create this new triangle. So you see, these are all very simple calculations that we can do, and then we can clip our triangles, and we already saw that this of course works for a single triangle, for a situation where the result is a single triangle, but it also works for a situation where we have 2 vertices inside of the view frustum. We just have to make sure that we cut here then this object again in 2 triangles. It also works for situations where we have triangles that are intersecting not just with one intersection one of the clipping planes like we see here, but also with, for example, 2. We just need to make more create more triangles when we clip them off. So first we clip, for example, against the left side here, then we get 2 triangles. Then we clip against the bottom side where we have then 2 triangles clipped against it, and in one case the result is another triangle, in another case the result is 2 more triangles. Good. And of course it also works with 3 clipping planes. So yeah, I leave this is pretty simple, so I leave this as an exercise. And of course it also solves this case that we saw before, which was actually the case I used to introduce this, how we are doing the clipping against the different planes. The interesting thing that you see here, or might have noticed when I bring up this old image here from previous, that at some point in the illustrations I switched from this shape of our viewing volume to this shape, which is the shape of the orthographic view volume, which brings up, of course, an interesting question is, when do we do the clipping? Because you would assume, of course, the clipping, we're not processing these points, or we're not drawing these points on the screen anyhow, so it would be seems to be the most obvious to do the clipping as soon as possible, because why should we process all this in our graphic pipeline and then in the end cut it off when we're not showing it on the screen anyhow? So why it seems to be the most obvious to do it at the very beginning. However, the problem is, or not the problem is, but an issue is that these plane equations are of course much more complicated than the plane equations here, because of course we do all this transformation to make the calculation easier. So doing the clipping with the orthographic view volume would be much easier from a calculation point of view than the clipping here, because the line equations that we have, that's the illustration of the question where we want to do the clipping. Do we do it with the original view frustum, or do we do it later after the homogeneous divide when we have the data in the orthographic view volume? And that has the advantage, of course, that the plane equations become quite simple. So you see here, for example, for the left side, I have an illustration here. The left side of the view frustum is illustrated by this plane minus x plus L. So we have here, I think there was an exercise in the very first tutorial, what is the equation of a plane that is parallel to the xy plane or something like that. So all these situations where planes are parallel to one of the axes are, of course, special cases that look a little different than the general form of a plane equation. But if you look at it, of course, it's very simple and straightforward to see how what kind of plane equation we have here. So if this is the top view now in the direction of the z-axis, if this is our plane here, then the left plane, then of course this is the distance L. And then, of course, we can say if a point has an x value here that is the same as the negative L value, then, of course, this equation is 0. And, of course, it doesn't matter what the y and the z value is, as long as the x value is the same as the length, the left side, this value L here, then, of course, the point is on the plane here. So this is obvious to see that this is the equation of the left plane, and also for the other planes we see it quite easy in the same way, quite easily. And that, of course, allows us to calculate it very easily. But there is one problem with this, of course, and that is the thing related to what we discussed last time when we introduced this homogeneous divide. I said that we cannot do this projection to the orthographic view volume in a way that preserves the set values in the same way, that they keep the same relation to each other as the x and the y values. With matrix multiplication. It just doesn't work, but it also doesn't need to work because we just need to preserve the order of the set values. And then I illustrated this, that this is the result that we get for the set values. And actually I illustrated it with a little, it is not really incorrect, but it's kind of a little, not 100% accurate. We see the set values are mapped to a new set value that is proportional to 1 divided by set, or it's actually to minus 1 divided by set. That was the little inaccuracy that I did last time when I drew the image, because all the n plus f and n are all constant values, so the set dash value is proportional to -1 divided by set. So proportional to 1 divided by set is this, -1 divided by set is that, and if we add here a constant value, of course then the function just shifts up. So we have, this is basically the mapping that we get from the set value to the set dash value if we do the homogeneous divide. Now if you look at this, this is an illustration. I hope you can see it. It's an image from the book. I put some color there to illustrate it a little better. So we see this here is the mapping of the set values from set to set dash with these black functions here. And now we have an illustration here at the bottom. We have here our I vector. So we place our virtual camera or our eye here, look in that direction, and here we have a triangle which is partly behind us. Now the first, the two vertices in front of us, the B and the C, are within the view frustum, which is here the near plane and here the far plane. So we see those are mapped to the two different points that are also inside of the view frustum, which of course has to be because we have proven, we've made a formal proof that showed that within the view frustum, the points stay within the view frustum, and we've also shown that the relative order to each other is preserved. So those 2 points are mapped appropriately, but this point here is outside of the view frustum, and this is exactly the case we excluded, and this is also why it is excluded, of course, from the proof that we did. And you see now, if we map this point here, this set value, to the set dash value, then this negative here, we have small set is smaller than 0, is suddenly mapped to a positive set value. That means the point that is behind our eye suddenly jumps in front of our eye and of course creates a wrong triangle. And another problem we see here is here at this position. If we had a triangle that is very close to our eye, or where one point is very close to our eye, then here the negative value, the positive value becomes negative. Here we have a positive set value that will then become a negative set dash value. So it moves from in front of our eye to behind our eye. So we see here we get these artifacts here if we do the clipping after the homogeneous divide. So we have to do it before with these planes that are a little more complicated. Well, I'm saying a little more complicated now because of course they are more complicated, but the calculation of them is actually not that complicated because we already have, when we create the planes for the orthographic view volume, we already have matrix for that. So to create these other planes, we just need to do apply the inverse matrix, and then we can create these planes, and then we can do the clipping. So the planes are more complicated, but the calculation actually isn't that complicated. But there is, of course, is fortunately another way to do it by using still very simple planes, and that is directly before we do the homogeneous divide, because then our plane equations look like this, and then we can do the clipping very easily. To illustrate this, let's look again at the left side. What we do is with the homogeneous divide, or with this extension of the homogeneous coordinates, we represent a point in the traditional way of the homogeneous coordinates with the 1 here by a point where we have this value w here, but then also of course all the points here are multiplied with this w. So by the matrix multiplication we get a value here that is not 1 but that is w, or w dash, and then dash because we also have the dashes here, because then these points here do not represent the outcome of our transformation x, y, and z, but they represent the outcome of our transformation divided by this w, which is then this step of the homogeneous divide. And when we do that, then of course we have again the 1 here, and these are then the resulting vertices of our triangle that is appropriately projected onto the screen. Now we see here this homogeneous divide, so from here to here what we do is we multiply with 1 divided by w dash. But that of course also means if we have this plane equation and want to create this one, we just multiply it with w dash, And then of course this here is clear. It becomes Lx dash. Now the x becomes x dash is of course also clear. If you think about what this x is p dash x divided by w. Now if we put that, if we multiply that with w, then of course we get this px dash, which is of course exactly this value that we have here. So that's why I wrote these down here. So you see we can very easily create this plane equation and then use them. And of course we can use it before the homogeneous divide, because the problem that we have, why we cannot do it after the homogeneous divide, this problem only appears because we make this division, because the division changes then the set value in a way that is unfortunate for us in this situation. So that's why of course doing it directly before the homogeneous divide actually works. And fortunately the plane equations there are equally simple as after the homogeneous divide. Good. All right. Now this is a little an extension. That's I'm going to talk about two algorithms now that are not covered in the book, but they are also important for graphics, not necessarily for 3D clipping, but also, for example, for drawing programs where we also have to do a lot of clipping. So clipping in general is very important in graphics, which is why I also want to discuss the case of clipping arbitrary polygons. So these are two algorithms that are not in the book, but I think that the slides should be enough to understand it, or if you're not, you can just Google it and you find a lot of information online about it that you can also look up if you need more information. Good. So the idea is we have a polygon in 2D that we want to clip against a clipping area. So I'm restricting myself for the examples here to a rectangular clipping area, but in basically any kind of clipping area that is bounded by lines or planes, line equations, then we can use for the clipping here. So the idea is we have a polygon like this blue here, which that is defined by certain lines, and then a clipping area, and we want to clip the polygon against this clipping area. And of course the most obvious way to approach this would be, let's just do the same that we do with the triangles. We just clip the polygon against each side of the clipping. So against each, we extend each side of the clipping area, and then we clip the polygon against each of the sides, and then we create our clipped polygon by that in the same way as we did it with the triangles. And of course that works, and that is called the so-called Sutherland-Hodgman algorithm. So let's see how we can phrase that in pseudocode so we can implement it. So first of all, we extend the upper side of our rectangle, or the first side that we start with of our clipping region. If we don't have a rectangle, in this case it's a rectangle, so we extend it. Then we start on one vertex of the polygon and follow its path. So for example, we start at P0 and then we follow the path here until repeat till we start and repeat till we're back at the vertex P0 where we started. And while we are doing this, every time we cross, we calculate the intersection. We check if there is an intersection here. If there is, we calculate the intersection point and enter that into our sequence of points that we are crossing. So we start with P0 here, then we go to P1, but when we do that, we see P1 is on a different side of this plane. So we calculate the intersection point and intersect it here. In between, of course, because we know that we are in between those 2 points, because we know that the points are on different sides of the plane. Then we come to P2, then P3, and then P4, P5, and P6, and then we're back again at P0. And of course here we don't have this I in here. Oh wait, I forgot one. P2, we also have here, of course, let's call it I0 dash. because here, of course, we get another intersection point. So for now, we just extend, we're checking against this clipping plane here. So of course, we only get these two intersection points. We don't know about this one yet, only these two here. But this is, of course, one that I forgot to create. And no one protested. You should pay attention. Good. And then, of course, we have these entered, but since we also checked on which side of the plane it is, and we also know, of course, that these two are outside. So what we do now is we just exclude this part here, and then we have a new polygon, which is, of course, everything but this part here. And then we do the same against, do I have another image? No. We do the same against this one, where we again start. Now we're walking from I0. Wait, let's... Oh, no, that doesn't work. Anyway, so we remove that. So, and now we're walking along here. We have extended this one. And then we see, of course, we're creating here two new intersection points, I1 and I2. So from P0, we get to I0. And then we have a new intersection point here, which is then called I1. Then we come to this intersection point here, I0 dash, and then to P3, and then to I2, which is a new intersection point that we find here, then to P4, and then of course it continues here till we're again at P0. And then we see we have these new two new intersection points that also indicate that this part here is outside of the viewing plane, so we exclude it here, and we get the polygon, which is, yeah, I'll leave it as an exercise to write it again. Write it clearly, neatly, and in a readable way. Good. All right. So you see, this is pretty simple and pretty straightforward. I just wanted to go through one of the steps to really show each example of it. So we see this works, but unfortunately, it doesn't always work, because we have situations like this where the algorithm, if you apply it, I'm not going to do it here, but you have it in the tutorials, and of course you can also use this as an example to apply it yourself as an exercise, which is a very good exercise. But if you apply it, this algorithm to it, you will not get something like this, which is of course what you would want. What you get is something like this. So if you draw that, you get this extra line here, which is of course not what we want. We want to only have these two here. So this is a problem with this algorithm, and this is why we often use this other algorithms, and one of the most popular ones is the so-called Weiler-Atherton algorithm, which should I make a break here? No, I probably make a little longer the first part and then cut the second part a little shorter. So because I don't like to stop, make a break in between one algorithm. So let's start here. Yeah, so the Weiler-Atherton algorithm, the basic idea of that is that we create a graph that represents our clipping area and our polygons in a way that we can very easily extract these clipped polygons from the graph. So what we do is we create a graph that represents the polygon. So we start by making a graph that contains polygon vertices. So for each polygon here, for each vertex of the polygon P0 to P6, P8, we see we have a vertex here. So that is the white ones here, P0 to P8. We create vertices for the clipping region, which are these here, the green ones. And we create vertices for the intersections, which are the red ones. I will explain later why I use different shades of red here. But first of all, we have these different types of vertices, and now we want to put edges into the graph that represent the shape of the polygon, the shape of the clipping region, and their relation to the intersection point, because that later helps us extracting the clipped polygons. So first of all, we start by integrating the edges that represent the shape of the polygon. And that would of course be, if we start with P0, that would be directed edges where we go from P0 to P1 to P2 and so on till we're up at P8, and then we go back to P0. But of course that only represents the polygon. If we want to use it to get the clipped polygons, we need to also see how the intersection points relate to that. And that is why we say here, when we go along the boundary of the polygon, we include the intersection vertices. So what we do is here, we start again at one point, and then we walk along the borders of the polygon until we reach the end, and then we include each transition to another vertex by an edge, a directed edge in the graph. But we also include the intersection point. So from P0 to P1, we get an intersection point. So we don't go here, but we go in the graph, we go here. Then from I0, we reach P1. So we go here. From P1, we go to P2. From P2, we go to P3. From P3 to P4, we see that our intersection test shows that we're intersecting here. So we calculate the intersection point and include that in the graph. Then we go to P4, then we come to P5, then we get another new intersection point that we enter, then we go to P6, then we go to P7, then we go to P8, and then we get another intersection point which is I1, and then we come back to our original starting point of the polygon. So we walked around the whole polygon and included the intersection points that are represented now in the graph. And now you see that from the graph structure we could reconstruct the shape of the polygon. And now we do the same for the clipping region. So you see here, we also walk along the edges of the boundary of the clipping region. So we start, for example, with R0 and walk around here. And now we have already calculated these intersection points. So when we're passing here, we're also passing these intersection points. And that means we can also include them in our graph. So from R0, we come to R1. From R1, we come to I0. From there, we come to I1. From I1, we come to R2. From R2, we come to I2. From I2, we reach I3. From I3, we reach R3. Here, and from R3 we reach again R0. So let's see, did I draw this correctly? Yeah, I think so. Good. So so we see here how we can create this graph, and this graph now represents both our clipping region and our polygon, and the relation to the intersection points. And with the relation to the intersection points, of course, we get also the relation between the clipping region and the polygon. So what we do now is we use this graph to create these clipped polygons, and we do this by taking advantage of what I ignored so far, which is this one step here, that we distinguish between outgoing intersections and incoming intersections. And I made this by giving them a color red or light red or pink in this graph image here. So if we're going from the inside of the clipping region to the outside, this is an outgoing vertex, illustrated red here, because also here from when we walk along the polygon, we go outside of the clipping region. And in the other case, we have an incoming vertex because we go from the outside to the inside of the clipping region. That also illustrates that it's important that when we apply the algorithm, that we in both cases walk in the same direction. So for example, in this case, both times we walked clockwise, and that is important because otherwise we run into problems when we use this graph to extract the polygons from the graph, the clipped polygons from the graph. And because we do this by first taking an outgoing intersection vertex and then walk along the boundary of the clipping region, which are the black edges in the graph. So we start with an outgoing edge. So for example, I0. And I purposely did not draw the image here or put the image here, so you see that we can really extract it just from the graph. We walk along the boundaries of the clipping region, so the black vertices in this graph here. So we get as the next one an I1. And then we do this until we reach an incoming intersection vertex, which is what we do now here, I1. And then we switch to not walking across the boundaries of the clipping region, but to walk along the boundaries of the polygon. So we follow the red edges here. So we come to P0. And then we continue walking here until we reach the starting vertex, which in that case we already did after these few steps. So this is then our clipped polygon. And if you look at the image, then you see, of course, that this is correct. This gives us the first clipped polygon. In the second case, we have one vertex more here. But if you apply the algorithm, then you see that this will again result in the correct polygon here. Now there is one step here that I excluded, which is, or not excluded, or that one case that we didn't need. We didn't need this changing from polygon boundary to clipping region step here, because that is a case that didn't happen here. But you can should I give you an example, or should I refer to the tutorials? Does anyone have an idea? Just think about different, more weird cases. For example, something like this. Then you will realize that you have to make more switches between the left and the right side here, or the black and the red edges. Good. But this is an algorithm that works with all kinds of polygons. So we see here it's more complicated in the Sutherland-Hodgman algorithm, but it can be implemented with a graph, or it can be represented with a graph, which means it can also be very easily implemented and gives us then the correctly clipped polygons. Good. Yeah. And actually that worked out quite well. So are there any questions? If not, then it's time for a break.